Okay, one final section of this chapter. We're going to talk about binary star systems and then talk about the age of star clusters. First up, binaries. Now, in a binary situation where two stars are orbiting a common center of gravity, each star kind of has its area where its gravity is dominant. It's a gravitational sphere of influence that we call in astronomy a Roche lobe. Yeah, same guy that we had the Roche limit around planets. This is the Roche lobe, a gravitational sphere of influence. So, in some situations, the two stars basically leave each other alone. They orbit each other, but each star evolves independently. The more massive one would evolve first and become a red giant and a white dwarf, for example, and it just wouldn't affect the other star. And the second star then would evolve and not be affected by the first one. That's called a detached binary, but that's kind of boring. It gets more exciting when the two Roche lobes sort of overlap. When the stars are, for example, close enough together that the Roche lobes overlap, in which case, if one star evolves first, the more massive one, it swells up into a red giant, let's say, its material can start streaming over onto its partner star. The point where the two Roche lobes overlap, by the way, would be the Lagrange point, the L1 point specifically, and that's where the mass transfer would occur. So you have the outer atmosphere of this red giant pouring over onto this other star, and that's going to sort of change the future trajectory of the way each star evolves. Anyway, one of the things that can happen then is that the second star, the lower mass star, may gain so much mass from this process that it too will start to evolve. It may speed up its evolution and become a red giant sort of ahead of time. And if they both become red giants and they kind of overflow, we call that a contact binary. I used to call it a flaming peanut. I had a great picture of this on the old laser disc years ago that looked like a peanut on fire. It would be kind of a common shell, and inside this peanut shell, you'd have the core, the nucleus, the core of two stars, but the atmospheres would seem to overlap. So you have two red giants together kind of overlapping. That's called a contact binary. I'll show you some pictures in a moment. First, I want to talk about an interesting situation here with a star called Algol. Algol is a pretty well-known star in the constellation Perseus. And Algol contains a 3.7 solar mass blue giant paired up with a 0.8 solar mass red giant or red subgiant. Why is this unusual? Well, you see, we always say that the high mass stars are supposed to evolve first. Well, Algol looks like it's breaking the rule because the 3.7 solar mass blue giant is still on the main sequence. It hasn't evolved yet. And it looks like the 0.8 one has skipped its turn and already is evolving off the main sequence to become a red subgiant. That doesn't make sense. It's like the little brother star grew up first. So what happened? Well, what happened was this. When these stars were born, when they were created, the 0.8 one originally was the heavier star. That's the only explanation that makes sense. It was the big brother star when it was born, but its material at this point in time has been pouring over onto its sort of sibling star. So we've caught Algol at a very unusual time here, where the one star has evolved into a red giant, but its material has flowed over onto the blue giant. Pretty soon that blue giant then is going to evolve. It may blow up or it may become a red giant. And if it becomes a red giant too, then you may have a contact binary there. Let's take a look at what these things are supposed to look like. Take a look at the upper left. Here's a mass transfer where you have a red giant and its material is pouring over through the L1 point and swirling around its partner star. Now that swirling area of debris is called an accretion disk. That'll be important in the next chapter, an accretion disk. And as I mentioned, if they both evolve, they can have this common envelope around them kind of a flaming peanut there, a contact binary. We have the cores of the two stars that share a common envelope, a common shell. Okay? One more interesting thing about Algol. I said it's in the constellation Perseus. Well, in probably the most famous story in mythology, Perseus is the hero, and he very famously kills Medusa. Medusa is the one that has snakes for hair and can turn you into stone, and he uses his shield as kind of a mirror, and that turns her into stone. And so he takes her head around with him, and he can use that as a weapon, and he uses that against the big monster, whatever. Here's what I think is interesting. In the sky, the star that represents Medusa's head is, you guessed it, Algol. Now, Al means the in Arabic, so Algol means the ghoul. So the ghoul, of course, is Medusa. I just think that's pretty cool. Algol, the ghoul. Here we see, again, an accretion disk swirling around a partner star there. Okay, one more section here of the chapter, the age of star clusters. Scientists, astronomers love to study star clusters because those stars have a lot of things in common. They were born at the same time, for example. They were born of the same material, and so forth. So they're a nice homogeneous group of stars. But the more massive stars are going to evolve first. And so which stars have evolved and which stars haven't evolved allows astronomers to very easily determine the age of the star cluster. Let's take a look. Here's the Hyades Cluster. Almost all of its stars are still on the main sequence. You see only a few right up in here have evolved into red giants. So the main sequence cutoff, if you look at the cursor there, that's what we call the main sequence turnoff point. And you can see that only the very hottest, most massive stars haven't evolved yet on the Hyades. So the Hyades is a very young cluster. Okay, if this represented a neighborhood, maybe this is a neighborhood where only a couple people have reached retirement age and everybody else is still of working age and school age. Versus, let's say we looked at a different neighborhood and it looked like this, where a whole bunch of people have gone into retirement. See, all these stars are becoming red giants and the main sequence turnoff is way down here. So that means it's a much older cluster. Matter of fact, I know the age of this cluster because the stars that are getting ready to evolve are at about 6,000 Kelvin. That's the same as our sun. And since our sun is going to spend 10 billion years on the main sequence before it evolves, it means that this cluster is about 10 billion years old because stars just like our sun are getting ready to evolve and become red giants. So here's a pop quiz for you. This is the famous double cluster in Perseus. Here is its HR diagram. Do you think it's a young cluster or an old cluster? Well, it's a pretty young cluster because only a few of them have become red giants, and the main sequence turnoff here is at very, very hot stars. So you still have a bunch of stars on the main sequence. And that is it for this chapter, Chapter 11, Stars. And we're just going to end with some beautiful stars here in Kimball's Cascade. Really beautiful shot of stars. Thanks for listening.